Hello, my name is Helen and my metric number is 141848.
And my name is Daniel Shakiri bin Zainal, matrix number 144531, and we are from group 17. First of all, let me introduce to you a little bit about our integrated design. So our integrated design is about the production of propylene. The process involves a lot of unit operations such as cooler, heater, compressor, condenser, boilers and reactors. At some unit operation, heat exchangers are used to increase the temperature or lower down the temperature for the condition that we wanted. Designing the suitable and appropriate heat exchanger is a must to ensure that the output conditions will get the product that we wanted.
In this integrated design, the heat exchanger assigned to our group is cooler. The objective is to design the most economical heat exchanger unit from the available process parameters and conditions. In order to design the most economical heat exchanger, we have researched and obtained some useful information for designing the heat exchanger. We chose shell and tube with counter current flow as it is the most widely used in cooling system. We set the cold fluid, the diameter of the tube, the length of the tube limit and the velocity of the stream are assumed.
For milestone 1, we were assigned to list down the heat exchangers available in the process flow diagram. So this is the process flow diagram. So according to our discussion, there are a total of 7 heat exchangers involved in this chemical plant. These are B101 feed furnace, H101 feed preheater, H102 cooler, H103 cooler, H104 C3 splitter heater, H105 C3 splitter condenser, H106 reboiler for C3 splitter.
At this point, I would like to share the block diagram of the propylene production that we had done previously in milestone 2. And we are assigned to do the calculation for the H102 cooler. This is the enlarged H102 cooler. We have the stream 11 has the inlet and the stream 12 has the outlet. This is the table of the condition inlet and outlet stream, which is very useful to the next part, which is calculation of the heat exchanger. So this table contains of temperature, pressure, mass flow rate and mole flow rate, and also the enthalpy of the stream 11 and stream 12. We focus on the calculation part. So before we start the calculation, we need to do several assumptions. So this is the 5 assumptions that we need to consider in our calculation. And for allocation part of the fluid, we took the dirty water as our cooling medium, which is normally known as the corrosive, or we allocate it in the at the tube side. First step, we need to find the heat transfer. So we can get the heat released by the equation of delta Q equals to delta H, and the heat absorbed, as we assume that there is no heat loss to the surrounding. So we assume that the heat absorbed is equals to heat released. Next, we determine the outlet temperature of the cooling fluid. We do the assumption on the cooled water, and the parameters we substitute in the equation. We get the outlet temperature. For the step 3, we find the log mean difference by using this equation. And step 4, find the correction factor F. In order to get the F, we extract this figure from the Paris handbook. And step 5, we estimate the density of water. This is of water can extract from the table A9, which is took from the Holzmann book. And step 6, we do the assumption on the parameter of the heat designing. Step 7, we do the calculation on the based on the case. So case 1 we do for the 1 shell pass with 1 tube pass. Case 2 we do for the 1 shell pass with 2 tube passes, and case 3 we do for the 1 shell pass with 4 tube passes. In order to get the suitable heat exchanger, we compare the 3 cases. So according to the tube length of tube limitation, which is 6.96, the most suitable is the case 2, because according to the heat exchanger design book, the most economically heat exchanger must possess a small diameter and long tubes. So the case 2 is the most convenient for our heat exchanger.
Okay, for this integrated design, we choose to use the shell and tube heat exchanger with 1 shell and 2 tubes pass. counter current flow of cooling water is used to make the temperature difference uniform between the fluids and along the fluids. As compared to plate heat exchanger, this kind of heat exchanger are more appropriate to use and widely used in industrial applications. It is also very flexible to designing the coolers as the heat exchangers. Counterflow also increase the efficiency of the heat exchanger per unit area.
From the calculation, case 2, which is one shell pass with 2 tube passes, is chosen because the length of the tube is nearer to the length of the tube limit. The table shows the summary of the calculation of case 2 in terms of the total area of the heat exchanger, the area of the tube, the number of the tubes, and the length of the tube. Next, the total size of the heat exchanger can be determined in terms of the volume, which is a product of the total surface area and the length of the tubes. In conclusion, there are many types of heat exchangers such as plate and frame, double butt, coil, air-cooled, and shell and tube. The working principle of the heat exchanger is same, which means the heat is transferred between two fluids without mixing them together. By revisiting and redrawing the process flow diagram, we have a clear understanding of the process components and conditions. A number of sources and books are used to determine the final calculation of the design. For this cooler, a shell and tube with one shell pass and tube passes is selected.